Great, so today I'll be talking about joint work with Klivans and Raghu Meka on the question of learning deep Relu networks. In this talk, we're going to be interested in the familiar task of Pac Learning, namely given labeled examples drawn from some distribution, output a predictor that achieves low test error with respect to that distribution. Now, the practitioner's tool of choice would simply be to run SGD to train a large deep neural network on these examples and use that as the predictor. It's no secret that this works great on real-world data, and the central mystery that's been the focus of a ton of work over the last few years is why this approach seems to work so well in practice, not only from an optimization perspective, but also from the generalization perspective that we focus on. Now, apart from asking what's so great about this particular algorithm or family of algorithms, one can also ask how distributions over real-world data seem to evade well-known worst-case hardest results for learning neural networks. That is, for which distributions D do there exist any algorithms for the above task? Questions 1 and 2 often go hand in hand with each other in terms of techniques, and at their core, I'd argue they're motivated by a much more ambitious agenda. Namely, can we design better and more principled algorithms, ideally with provable guarantees, that outperform existing techniques on any number of axes like speed, sample efficiency, robustness, etc. Now, any theory that satisfactorily answers these three questions had better explain the following special case, namely when the labels are actually exactly given by some unknown neural network F. Okay, so if I tell you that the ground truth is completely explained by some unknown parametric function, can I learn that parametric function? So this is the setting we'll consider in this talk. Let me first define what a neural network is. Okay, so at a high level, a neural network is just a composition of linearities and nonlinearities. Okay, so given an input x, which is just some high-dimensional vector, the neural network computes the output y as follows. It multiplies the vector x by some weight matrix to get some new vector. It then passes that new vector entry-wise through a nonlinear function, sigma. That gives a new vector of activations that then get passed through another weight matrix W2, then through a nonlinearity, etc., until at the very end, we take an inner product between the final weight matrix, which is just a vector, WL, with the prior vector of activations to get the final output Y. Okay, so that's a neural network. And in this work, we're going to focus on Relu networks, namely neural networks where the activation sigma is given by the popular Relu activation. And for those unfamiliar, the Relu activation just sends a scalar input z to max of 0 and z. Okay, we can write this network more compactly as f of x equals the following interlaced matrix multiplication and nonlinearity. And the relevant parameters that we'll consider are the ambient dimension d of the input, as well as the so-called size of the network. And the size of the network is simply the number of columns across all of W1 transpose to WL-1 transpose. You can think of this as really the number of activations in the entire network. Okay, so that's what a neural network is, and our goal is going to be the standard one, namely Pac Learning. So given examples x1, y1 to xn, yn, which are labeled according to some unknown neural network, F, and where the xi's are drawn independently from some known distribution d sub x, our goal is to output a network G, which is close to F in L2, in the sense that the expected square difference between f of x and g of x with respect to this distribution d sub x is small. Okay, so there are plenty of well-known worst-case hardest results in a distribution-free sense for learning neural networks, and so we're going to adopt the standard setting where we place some benign assumption on the underlying input distribution. Namely, we're going to assume that the input distribution just comes from standard Gaussian in d dimensions. Okay, so what's known about this this kind of problem? So it's safe to say that essentially all existing works on provably learning Relu networks are focused on the depth at most 2 case, which looks a bit like this. Okay, so a depth 2 neural network you can think of as simply a linear combination of nonlinearities applied to inner products of the input with various vectors w sub I. Okay, and the existing techniques, at the risk of oversimplification, really fall under the following 3 buckets. There are those that rely on tensor methods and dimensionality reduction via Stein's lemma. There are techniques based on kernel methods, And then there are works which analyze the dynamics of gradient descent. So the techniques based on kernel methods have one drawback, which precludes them from application to our setting. Namely, they require that the input is bounded in norm by some quantity which is dimension free. Okay, so that precludes, for instance, the Gaussian measure. What about techniques 1 and 3? One big drawback for these results is that they all need to assume some subset of the following conditions. Namely, either that the output weights, lambda I, are all positive, and or the input, the weights in the input layer, namely the WIs, are well conditioned or approximately orthogonal. Okay? And so a natural question you can ask is, are these assumptions fundamental, or can we design Pac Learning algorithms that don't need to work with these kinds of assumptions? And now it turns out that there's actually a pretty good reason why all of these papers need to make this kind of assumption. And this is what one could call the so-called CSQ barrier. Okay? So the reason is that all of the existing approaches based on Stein's lemma and gradient descent could actually be implemented using a noisy oracle that can answer correlational statistical queries. So rather than work directly with the samples, it suffices for these algorithms to have access to the following oracle. Namely, the learner can feed in any function from RD to R, and the oracle tells them the expectation of y times that function applied to x plus some small adversarial noise. Okay, and so you can certainly implement a correlational statistical query using sample access, but it turns out these algorithms only need to work with this particular oracle in order to get their guarantees. So why are these algorithms based on Stein's lemma CSQ? Well, Stein's lemma is really, how they exploit Stein's lemma is that there exists some tensor-valued function, Sm of x, such that the correlation between y and Sm of x is equal to some linear combination of tensor powers of the weight vectors. Okay? That's the whole premise of these algorithms based on tensor methods. On the other hand, we have algorithms based on gradient descent, often with respect to square loss, because we're in the regression setting. And here, if you look at a single gradient step, you get, a term in blue, which is like a CSQ, and then one term in gray, which is just some statistic of x. And recall that we know the distribution over x; it's just Gaussian. So in principle, we could evaluate this statistic exactly. Okay, and so what is known about algorithms that use CSQs? Well, just 2 years ago, it was shown by two separate groups that actually no algorithm that only uses CSQs can run in time better than roughly d to the size of the network, even for depth 2. Okay, so a basic question to ask is, can any algorithm, maybe one that doesn't involve making CSQs, learn general depth 2 networks in time better than d to the s? And more ambitiously, can we hope to get such guarantees even beyond depth 2? Okay, so now I want to turn to what we actually show. So of course, there's going to be some need for a sense of scale in this question, right? So if the weight matrices were arbitrarily large, then the runtime will be arbitrarily large in order to get, a fixed level of accuracy. And so let's let our notion of scale be the product of the operator norms of the matrices, of the weight matrices. Okay, we'll call that B. Okay, so the first thing we show is that actually any feed-forward network of arbitrary depth, you can actually Pac learn to error epsilon in time, which is a fixed polynomial in the dimension, times some exponential function in the other parameters, namely the size, the scale, and 1 over epsilon. Okay, let me emphasize that this is a fixed parameter tractable guarantee, because if these other parameters, namely SB and 1 over epsilon, were all constant, then our guarantee is a fully polynomial time algorithm for neural networks. We can do slightly better if we additionally assume that the network is, say, lambda Lipschitz, then we can replace this scale parameter b by lambda. And note that b is always a sort of naive upper bound on the Lipschitzness. And the only thing we pay is a slight logarithmic overhead in the exponent. Let me emphasize that actually some dependence on lambda is necessary even for depth 2. And the main takeaway from this theorem should be that this is the first example of a neural network class that one can learn efficiently, but provably not via noisy gradient descent. Okay, So how do we show such a theorem? So the first observation is that f is really secretly a low-dimensional function. Okay, note that how it interacts with the input is exclusively through this weight matrix W sub 1. So f is something that we would one might call a multi-index model or a subspace junta. It only depends on the projection of x to the row span of W1, namely to some smaller dimensional subspace. Let's call it U. Now, the upshot is that if you could identify this relevant subspace, U, then there's a simple algorithm to learn the rest of the function. Namely, you can brute force over the parameters of that low-dimensional function to find an approximation to the true network. And instead of paying exponential in the ambient dimension, you only pay in the dimension of this low-dimensional subspace. Okay, so the question is, before I want to learn this full subspace, how do I even find a single vector in this subspace? A natural first attempt would be to look at the following matrix-valued statistic, namely look at the correlation between y and xx transpose. And this minus identity is just some shift. Okay, and it's well known that if this function f satisfied those assumptions that I mentioned earlier, namely well-conditionedness and positivity, then actually this algorithm would just work. It would give you back some vector in this unknown subspace. But the key issue is that this matrix for general Relu networks can actually be 0. For instance, it's going to be 0 for the constructions in the CSQ lower bound. Okay, but there's a simple way to salvage this. Instead of looking at the inner product between y and xx transpose, let's look at the correlation between some function of y times xx transpose for some carefully chosen filter function phi. Now, if the matrix M were non-zero, it's a simple exercise to show that this the top singular vector of this matrix is actually still going to lie inside the relevant subspace, and so we would solve the task we were set with. Now the question is, how do I pick an appropriate filter function to ensure that this matrix is non-zero? To ensure it's non-zero, we're actually going to just ensure that the trace of the matrix is non-zero. Okay, so let's look at the correlation between phi of y and trace of xx transpose minus identity projected to the relevant subspace. And that's just going to be pi u x squared norm minus k. So this is the trace. Now, if the filter function behaved as follows, namely, it only gets activated for values x, inputs x, for which the projection has large norm, then what do we get? Well, if it only gets activated when the norm exceeds 2k, like in this cartoon, then the only contribution to this expectation comes from points pi u x, which have large norm. Okay, and so you can lower bound the trace by k times the expectation of phi of f of x times the indicator that the norm of the projection is large. Okay, now it's a bit tricky because we want this kind of behavior of phi, but remember phi doesn't depend directly on x, it only depends on x indirectly through the label y. So a naive way to ensure that phi has this kind of behavior would be to take phi to be just a threshold on the absolute value of y. The intuition is that if the label is big, that will only happen when the norm of the projection is large. Okay, in that case, you can lower bound this quantity by just k times the probability that the label is big in absolute value. And the final step would be to ensure that this quantity is bounded away from 0, and that's just some statement about anti-concentration for piecewise linear functions. And these details I encourage you to check out in the full paper. Okay, but the general intuition is quite clean. The idea is just that we're going to filter out data points with small labels, and this ensures that the data that gets left over looks noticeably non-Gaussian. So if I take the principal component of this matrix M, it's going to give me something in the relevant subspace. Okay, let me just convince you that this approach of taking of thresholding on the absolute value of y is reasonable. Like, why do we expect there to exist such a threshold tau? So here's a heat map for a 2D Relu network, and here is the sort of ball of inputs x for which the norm is small. And the idea is simply that if I threshold out all values which are at most this dark blue color, then what I'm left with is something that doesn't contain this problematic ball of points x with small norm projection. Okay, so this is just to convince you that there should exist some value tau, probably depending on k and depending on the Lipschitzness of the network, for which the program I described will work out. Okay, so that what have we gained from this discussion? We've shown that if you just form an empirical estimate for the following matrix M and take its top eigenvector, it's going to be close to the relevant subspace U because this matrix M is bounded away from 0. You might expect something even better. You might expect that maybe the full spectrum of M is going to reveal the entire relevant subspace U. Unfortunately, this doesn't seem to be true empirically for certain examples. And so we need some further steps to learn the rest of the relevant subspace. Okay, so what do we want to achieve? We found some relevant some relevant direction V inside of the subspace U, and we want to continue. We want to find something that's in U but orthogonal to the span of V. So here's the matrix we worked with earlier. A naive way of avoiding just finding the same vector V would be to project out V. Right? So let's project on both sides to the orthogonal complement of V. Of course, this isn't going to do anything. If this worked, then the previous matrix would have worked as well. But okay, let's keep these projectors. Now here's the key change. Instead of filtering on the absolute value of y, we're going to filter on a different quantity, namely the so-called residual. So what do I mean by this? Instead of absolute value of y, let's look at the absolute difference between y and, in some sense, the function we've learned so far. So here, pi v of x is just the projection of x to the direction we found so far, and we're applying f to that. Now, of course, we don't actually know the function f, but let's for now pretend that we have access to it. Now, if m prime is non-zero, then its top singular vector lies in the orthogonal complement of V. But as before, the hard part is really to lower bound this trace of m prime in order to ensure that the matrix is non-zero. It turns out the analysis for this is actually quite similar to what I showed in the previous slide, so I won't go into details about it. But again, the upshot is that this gives us a way to continue. Namely, if we form an empirical estimate for this matrix with enough samples and take its top eigenvector, I'm going to find a new direction inside the relevant subspace. Okay, there's a simple complication that I mentioned earlier, which is that we don't have access to this residual because we don't know f. Like, how can we actually evaluate f of pi v of x? Okay, but here's the key workaround. We know pi v because literal v was the direction we found so far. So in particular, f of pi v of x is computable by a bounded size network over a known subspace. And we can brute force search over all such networks over this known subspace because the subspace is a very low dimensional subspace. Okay, so that's the workaround around this sort of chicken and egg problem of not knowing f, but wanting to use this residual to learn f. Another issue is that we can only ensure that the directions we've recovered so far are close to the subspace U. And so actually one technical complication that is also sort of relevant to this previous issue of netting over networks is that we need this approach that I've outlined to be robust to sampling error. In particular, the key technical issue you need to address is, are Relu networks, and specifically, affine thresholds of Relu networks, stable under perturbation of the parameters. Okay. This is a bit out of the scope of this talk, but at a high level, we use insights from tropical geometry to answer this question. Okay, so the remaining time, let me just go over the relevant algorithm. So at a high level, we're accumulating a list of relevant directions, and we repeat the following loop. So let's let V be the span of the vectors we found so far. We're going to enumerate over all networks over this subspace V. And for each network in this net, we're going to check whether it's already close to the true network. And if so, we're going to just output it. Otherwise, we're going to form the top eigenvector of this matrix we've been talking about. And if this matrix is bounded away from 0, then we take that top eigenvector and we add it into our list. And we simply repeat this loop until finally we hit this exit condition where the f hat that we found achieves low square loss, and then we're done. Okay, so just as takeaways, what did we show in this talk? We showed that even though there are well-known CSQ lower bounds against learning even depth 2 networks, we circumvented this by using non-CSQ statistics and obtain the first fixed parameter tractable algorithm for learning general Relu networks. In particular, this gives a guarantee that provably can't be achieved using gradient descent. There are a variety of open questions. Can we get algorithms with more practical runtime? And more generally, I think this really opens up the potential for getting further separations between what you can achieve with popular heuristics like gradient descent and what you can achieve with general Pac learning algorithms.